I'm very excited to talk to you about information flow today, specifically type systems for information flow. Okay, what do information flow type systems do? Fundamentally, their purpose is to track the dependency structure of your program statically. And so if I'm holding a computation in my hand, I want to know exactly which bits of data that computation depends on. Okay. And this is super useful in a domain like security, right? Because I want to say that computations that depend on password information are not allowed to leak things to the internet, or they're not allowed to print things, right? But it's also useful for these data provenance and separation properties are also super useful for things like concurrent and distributed systems, right? And also for like program slicing and build systems and incremental computation, and surprisingly controlling unfolding in dependent type theory. And also, I found out 2 days ago, lineage tracking in CAD kernels, and also like many, many more things. So I'm going to take the security perspective in this talk because I think it's a particularly simple one to take, but I think it's helpful to keep in mind that information flow and dependency tracking is a broadly useful technique for lots of PL stuff. Okay. So I want to walk through how to reinvent our approach from scratch, basically, starting with parametric polymorphism. So if I give you the identity function, the standard polymorphic identity function, you know that the argument to it flows exactly to the return value, right? And if I give you this second function, you again know that the first argument to it flows exactly to the return value, and that the second argument is ignored. And if I give you this map function on lists, right, you know that the elements of the input list flow to the input of the higher order function argument to the list, or to the map function, and the return value of the map function flows into the elements of the output list. But what about something non-polymorphic, like inker going from int to int? So our first insight of 3 is to separate data abstraction from information flow properties. So we want to weaken parametricity to separate out the part of it that talks about information flow properties. Okay, and the idea is to tag types with dependency variables alpha. So instead of having alpha be the type, we're just going to have them sit next to the type. And so our type for inker is alpha into alpha int, and the alpha plays the same information flow role as before, but not the data abstraction role. What about something like the addition function on 2 integers, right? Here we have 2 separate dependencies flowing to the same return value, right? So how do we indicate the 2 dependencies on the return value there? And our second insight is to generalize from individual dependencies and types to sets of dependencies and types. Okay, so we're going to take each alpha and turn it into a dependency set alpha. And so we get this new signature for add that takes an alpha int to a beta int to an alpha beta int, where the return value here says, this is an integer that depends on data from sources alpha and beta. So it depends on both of the arguments. Okay, so let's do a more interesting example now that we've got some tools. Okay, we're going to start by declaring a variable pass that is a string initialized to the name of my cat, where the type declares that this string depends on or is password data. It represents password data. And we're going to declare another function, check, that takes in a password attempt as a string with dependencies alpha and returns me a Boolean with dependencies alpha and password. And these dependencies make a lot of sense because the body of the check function just compares the password attempt, which has dependencies alpha, to the pass variable, which has dependencies password, right? So you end up with 2 dependencies on this Boolean, which are exactly the 2 involved in the body. But to some extent, this checker is too conservative, right? Because if our policy is that we're preventing things that depend on password data from printing or leaking into the outside world, we can't actually return the result of the password check to the user, right? Because the type system will say, no, that's insecure, you're leaking data about the password. And so I'm oversimplifying here, but the solution to this is something called declassification, where you insert basically a cast into the program that says, I'm going to take a computation that is said to be dependent on this password label or this password dependency, and declassify is going to peel off the password dependency, and it's going to return the exact same computation to me. And this gets us the type signature we want, right? Because now we're doing the computation we want without the dependency we didn't want. But this is kind of unsatisfying as a PL person because this is just an unsafe cast, right? I'm massively simplifying, but at its most basic, it's some kind of unsafe cast. And there's this very conventional wisdom, that non-interference, which is the core soundness property of information flow, which says that basically dependency tracking must be fully faithful to what the program actually does, is sort of in conflict with declassification. It's in conflict with writing practical programs. So if you look at the Wikipedia page on information flow, it just says this outright, right? And to use a better source than Wikipedia, there's this wonderful paper by Sabelfeld and Sands from 2007 that says, this password checker program that we want to write is not possible under a fully strict non-interference policy, right? But I want to advance the perspective in this talk that non-interference is really a far more practical property than a lot of people give it credit for. And actually, using just the tools we've already introduced, it's possible to obtain the password checker that we want, which is a little bit surprising. So let's go through it slowly. So how do we get declassification for free, so to speak? And first, we're going to do some wishful thinking. So ideally, we want something like a password checker module. And what that module is going to do is it's going to declare a password dependency. And it's going to have a string field that plays the same role as before, pass, which is tagged with the password dependency. And when we use it in this usage here, and we concatenate that password field to some other string, we end up with another string that's dependent on password as expected. We have this check function where the Boolean return value now is not dependent on password. And maybe we also have this encrypt function that takes in a password-dependent string and encrypts it and returns us a string that is no longer said to be dependent on password data, right? Seems reasonable. Okay, the first step of getting there is to expose some lurking quantifiers. So when I showed you the type of the signature of the polymorphic identity function, right, I hid the quantifiers from you. But really, there's this for all alpha sitting in front of the type signature that binds the alphas in the type signature. And same thing for the map function, right? There's these for all quantifiers sitting in front of the signature that bind the alpha and the beta in the type signature of the map function. And when you graduate to doing information flow, it's the same idea, but instead of quantifying over types, you're instead quantifying over information dependencies, right? So these quantifiers bind the information dependencies, alpha and beta, in the signature of add. So our third and final insight is to take universal quantifiers on higher order functions and smash them together using the Girard encoding of existentials, which I won't explain, to get existentials. And the core insight here is that you've already sort of seen existentials in probably most languages you've used. They're roughly just modules or classes with a lot of asterisks, but like roughly. And so let's briefly review how modules work. So we've got this Q, which seems to be a popular data type here. And this type T in this Q module can be thought of as some existentially quantified thing. And from the client's perspective, it sees just the type exactly as I've listed, right? So the type T sort of represents some particular Q, and you can use these NQ and DQ functions on that type T to either string elements into the Q or extract elements from it, right? So this is familiar if you've used ML modules. But the signature that the implementation gets type checked against is the version of that signature where you substitute in for each occurrence of T in the signature this list T implementation type that is used by this naive Q structure implementation in the bottom, right? So its NQ and DQ definitions will be type checked against that substituted signature. So just to go back and forth once more, there's the client view, there's the implementation view. Okay, and it turns out that gives us basically exactly what we need to implement the signature that we wanted. So let's start implementing. And our first and really only interesting move is going to be to set the password dependency in the implementation to empty, right? And this is a valid move because when we generalized from individual dependencies to sets of dependencies, we made it so that each individual dependency variable in our type system stands for another set of dependencies. So this is a fine thing for us to do. And namely, when we do that, we make it so that from the perspective of the implementation, each occurrence of the password dependency in all the signatures of the password checker module are crossed out, they're elided, so the implementation doesn't have to care about them anymore. And so we implement pass again exactly as we did before by setting it to the name of my cat. We implement check exactly as we did before, where we just take in an attempt and compare it to the password field. And now check can just return a Boolean because note that password does not depend on the password dependency, right? From the perspective of the implementation again. And we can implement encrypt as just the ADA expansion of this GPG function, right? Because from the perspective of the implementation, what you're really implementing is just a function from alpha string to alpha string, and that's a really easy signature to inhabit. And I want to sort of declaim here that, of course, you could implement some totally insecure function that just leaks the entire password, right? You could export like the identity function from this thing, and it would just leak all the data, right? But the point of this technique is that if you want to do that, it has to be part of the abstraction of the password checker module like some random client of this thing is not allowed to do that. So there's this very nice modularity and composability going on here that's very familiar to statically typed programmers, right? And importantly, this all emerges just from those 3 insights we had. And I haven't added any of this to the language. This is purely just from those sort of totally uncontroversial insights. And that's sort of the bulk of the work, but I wanted to note one last thing, which is maybe actually familiar to those who are here for the modal effect types talk. We have this heuristic called dependency elision in our language that makes it so that when we can use these incur and add functions, or when I type these incur and add functions, I listed these dependencies on them that are kind of extraneous, right? They're not necessary because most functions use all their dependencies. And dependency elision is a recognition that, you know, maybe we don't have to list those like sort of boring dependency chains in our type signatures. And so when we write these sorts of functions, we can just elide them, right? And when after sprinkling on just a little bit more proof theory, it turns out that we can write the types of the map and fold functions on lists exactly as the bog standard types in our language, but without losing any precision in information flow tracking for special reasons. And filter is almost the same, but you have to have this beta tag on it. And the full explanation for why we can do that, and like a lot more really interesting tidbits are in the paper, so you should go read it. But the takeaway really is that. Right, and I'll take questions.
You have plenty of time for questions.
Hi, thanks. This is a really cool talk, really cool work. I'm a little bit curious what the actual non-interference guarantee you get out is, because it's not going to be the standard one. It's going to be non-interference up to some module boundary stuff, right?
It's actually, so if you look at our logical relation for non-interference, it's actually, if you remove the case of the logical relation for alls, it's exactly the same. All the declassification stuff is handled in combination with the case for alls and the case for function types, and our paper steps through basically the inner and outer perspective of the existential encoding, and shows how from the inner perspective you just assume that the implementations of these module signatures preserve non-interference, and from the inner perspective you like don't see the password dependencies, or you don't see the existentially quantified dependencies at all, so it's not relevant to non-interference.
Okay, very cool.
Thank you for the good talk. We've talked about this already, but I just want to hear your thoughts again about what other kinds of applications is there for a type system like this?
What other kinds of information? What other kinds of applications there for information flow?
Yes.
So a lot. I have a text file with a very quickly growing list of them, but one of my collaborators, Will Creighton, pointed me to this great page on the Svelte documentation, which is this reactive programming library for JavaScript, where it says, you know, if you do a reactive update inside a closure, the Svelte analysis is not sophisticated enough to realize that a reactive update actually has to fire. So like the recommendation of the documentation, at least when I looked at it a few months ago, was to go outside the closure and like do a self-assignment, like do like an x equals x to get it to realize that there's a dependency being induced, so a reactive update can fire. So if you don't do that, you're gonna have a dependency analysis bug. Also, if you have an information flow type system helping you with this reactive programming thing, you can compile it like way more efficiently, right? Because you don't have to do any of this like shadow DOM or tree diffing or any of that, right? You can just like make it so the compiler compiles your program such that when you touch some data, it like statically knows exactly what other data to reactively update. That's one really compelling example. All the credits to Will Creighton for that.
Okay, thank you.
Excellent talk. So I wonder, I think you have a dependency set. Is it associated to each argument or to each type?
Yeah.
So for example, if you have a function that takes a pair, like a pair of A and B, do you have a dependency set for A and B, or do you have a dependency set for the whole pair?
That's a really interesting question. So we connect the granularity of dependency tracking to something called polarity from proof theory. And so we support positive pairs in our language, or we support positive products in our language. So by default, like the dependencies of pairs are tracked coarsely across the entire pair. But you can choose yourself to give yourself negative products by just using the usual encoding, and then you're forced actually, because it's then a negative type, to track the dependencies individually for each projection. So it depends on the polarity.
I say thank you.
Yeah.
Okay, let's thank Hemant again.